Hi. So we were explaining the cycle notation. We have tried to explain it and because we can use this, and then now we will move further and try to talk about the properties of permutations. Right. So, and we present them in theorems. So the theorem 5.1 is products of disjoint cycles. Okay. It says that every permutation of a finite set can be written as a cycle or is a product of disjoint cycles. Now, this is very important and a very useful result, and I would like to prove it. So, I would like to present the proof. So, let's present the proof. Proof is the proof says let alpha be a permutation on the set. So, let alpha be a permutation on the set. When I sketch the proof, and then so you can also listen to me what I'm saying, and I'll try to speak the words but not write all of them. So let alpha be a permutation from A to A, where A is nothing but a set, which is right. To write alpha in disjoint cycle form, we start by choosing a member of A, say A1. So choose A1 from A and let that A2 is nothing but alpha of A1. Similarly, A3 is nothing but alpha of A2. Okay, and which is nothing but alpha square of A1, right? And so on. And so on until we arrive at A1 is equals to alpha power AM of A1 for some M. Okay, now we know that such an M exists because the sequence such M exists because the sequence A1 comma alpha of a1 comma alpha square of a1 must be finite, right? So there must eventually be a repetition and say alpha I of aj is nothing but alpha j of a1. This is, sorry, alpha I of a1 is alpha equal to alpha j of a1 for some I and j where I is less than j. Then we have a1 is equals to alpha power m a1 where m is nothing but j minus I. Now we express this relationship among all these a1, a2, am as that alpha can be written as a1, a2, am, and so on. The three dots at the end indicate the possibility that we may not have exhausted the set A in this process. So in such a case, we merely choose an element. We merely choose B1 from A, not appearing in the first cycle, not appearing in alpha, and proceed to create a new cycle as before. That is, we let and let B2 is nothing but alpha I should write appearing in first cycle, which is this one, A1 to AM. Now let B2 is nothing but alpha of B1, okay? And B3 is nothing but alpha square of B1, and so on until we reach that B1 is nothing but alpha power k of B1 for some k. Some k. The new cycle will have no elements in common with the previously constructed cycle. So if so, then alpha power I of A1 is going to be alpha power j of B1 for some I and j, but alpha power I minus j of B1 is equal to B1, and therefore B1 is nothing but A1 for some AT for some T. Now this contradicts the way B1 was chosen. So this contradicts the way B1 was chosen. And continuing this process until we run out of elements of A, our permutation will appear as by continuing in this way, our permutation is alpha is equals to A1, A2, AM, B1, B2, BK, and C1, C2 to CS. In this way, we see that every permutation can be written as the product of disjoint cycles. That's the proof. Okay, perfect. Now, another property is that this, sorry, it's the theorem says that disjoint cycles commute. That's very interesting property. Says the statement says if the pair of cycles alpha is equals to A1, A2 up to AM and beta is equals to B1, B2 up to Bn have no element or entries in common, then alpha beta is equal to beta alpha. Is equal to beta alpha. Now, prove this. So for definiteness, let us say that alpha beta are permutations of the set. Let alpha beta are permutations of the set S is equals to alpha A1, A2 to AM, B1, B2 to Bn, C1, C2 up to CS or CK. Okay, where C's are the members of the S left fixed by both alpha and beta. So we can say that where C's from S are fixed in alpha and beta, prove that alpha beta is beta alpha. We must show that alpha beta of x is equal to beta alpha of x for all x in S. Now, if x is one of the A elements, x is one of the A elements, say AI, then alpha beta of AI is nothing but alpha of beta of A, beta of AI, and beta will fixed AI, so that is alpha of AI, and that is some alpha of AI plus 1, right? Since beta fixes all A's, we interpret AI plus 1 is A1 if I is equals to M. And for the same reason, beta, so I can write that AI plus 1 is A1 when I is M. Okay, and then beta alpha of AI is nothing but beta of alpha of AI, which is nothing but beta of AI plus 1, and that is again AI plus 1. Hence, the function alpha beta and beta alpha agree on all A elements. Now, a similar argument shows that alpha beta and beta alpha agree on B elements as well. Hence, alpha beta is beta alpha for all A in S. Similarly, we can show that alpha beta is beta alpha for all B in S. And finally, suppose X is a C element. Suppose X is a C element, say Ci, then since both alpha and beta fixes C elements, we have alpha beta of Ci is nothing but alpha of beta of Ci, which is alpha of Ci, which is Ci, and then beta alpha of Ci is beta alpha of Ci, which is beta of Ci, which is Ci. And we are done. Perfect. Now, in demonstrating how to multiply cycles, we showed that the product of two permutations, here, alpha beta, this one, alpha beta, can be written in disjoint cycles in this way. So, written in disjoint cycles. Now, Now, is it only this is the advantage of writing the a permutation, like product or something in disjoint cycles? No. The next theorem shows that the disjoint cycles from has an enormous advantage of allowing us to eyeball the order of a permutation. So, theorem says that that the order of a permutation, and this is given by Ruffini, in 1799. Okay, the statement is the order of a permutation of a finite set written in disjoint cycles or cycle form disjoint cycle form is the least common multiple of the lengths of the cycles. Okay, now this here we use the number theory argument, and so we'll leave the proof for this one, but use this theorem and then compute the cycles. So let's give an example, which is number 4. We say that the order of the permutation 1, 3, 2, and 4, 5 is the LCM of 3, 2, which is 6. Okay. Similarly, the order of the permutation 1, 4, 3, 2, and 5, 6 is the LCM of 4 and 2, which is nothing but 4. Similarly, the order of the permutation 1, 2, 3, 4, 5, 6, and 7, 8 is the LCM of 3, 3, 2, which is 6. And yeah, so this is how we can use this theorem. Now, arranging all possible disjoint cycle structures of elements of Sn according to the longest cycle length listed from left to right provides a systematic way of counting the number of elements in Sn of any particular order. There are two cases: permutations where the lengths of disjoint cycles are distant, and the permutations where there are at least two disjoint cycles, ignoring one cycles, of the same length. The two cases are illustrated in, for example, 5, 6, and 7. Now, these examples are very important ones, and they and they contain the interesting and important information about the group Sn. So the example 5 says to determine the orders of 7 factorial elements of S7, determine orders of elements of S7 where 7 factorial, where order of S7 is 7 factorial, which is 5040. So there are 5040 elements of order S7. Okay, perfect. We only need only we need only consider the possible disjoint cycle structures of the elements of S7, and that's very strong result. Like you don't need to consider different elements, you don't need to consider anything else, you just need to consider all the possibilities of disjoint cycles, like, and then you can just tell them that okay, these are the elements which have, like, okay, these, like, m number of elements have order this and n number of elements have order this. You can say that, something like that. To do that, what can we do? So for convenience, we denote that an an n cycle is like this. Okay, then according then arranging all the possible disjoint cycle structures of elements of S7 according to the longest cycle length left right, we have what? We have 7, then we have, okay, let me write from here. We have 7, and then we have 6 and 1. Remember, the sum needs to be 7, right? And then we have 5, 2. Also, we have 5, 1, 1. There is no comma, so I can write it 1, 1. And then I have 4, 3. And then I have 4, 2, 1. And then I have 4, 1, 1, 1. Remember, I can write this over here and then this here, then, but I am writing them in this way just to save the space, and then just for the, just I want to be in the same screen. Okay, because these are going to be more. And then I can write 3, 3, 1, and then 3, 2, 2, and then 3, 2, 1, 1, and then 3, 1, 1, 1, and 1. Perfect. These are the possibilities with 3. Then we can write 2, 2, 2, 1. Then we have 2, 2, 1, 1, 1. And we have 2, 1, 1, 1, 1. And these are the 3 possibilities with them. And then you can say the last one would be containing only 1 cycles. Perfect. Now, from Theorem 5.3, we see that the orders of the elements of S7 are what? What? So, a cycle of this form have orders. No, that's going to be a wrong notation. So, but I can, oh, okay, I can say, I can write something here, maybe here. So, LCM of 7 is 7. Then LCM of 6, 1 is 6. Then LCM of 5, 2 is 10. LCM of 5, 1, 1 is 5. And then LCM of 4, 3 is 12. LCM of 4, 2, 1 is 4. And then LCM of 4, 1, 1, 1 is 4. Right? And then similarly, LCM of 3, 3, 1 is 3. LCM of 3, 2, 1, let's just say 1, sorry, there is again 2, is 6. LCM of 3, 2, 1, 1 is 6. LCM of 3, 1, 1, or I can also write the notation 1 power 4 is 3. And LCM of 2, 2, 2, 1 is 2. LCM of 2, 2, 1, 1, 1 is 2. And LCM of 2, 2, not 2, but 1 power 5 is 2. And then LCM of 1 power 7, that's not power, that's 7 repeats, 1 repeats 7 times is 1. And to do the same for the 10 factorial elements of the number, we would be nearly as simple. And that's, look at the importance of the result, which we have just presented here. The order of a permutation is nothing but the LCM of the least common multiple of the lengths of the cycles. Perfect. Now, what can you do to find out the number of elements in a set, in a group of certain order? So let's say example 6 says that determine number of elements in S7 of order 12. Now we know that there are elements of order 12 in S7 because there is a cycle 4, 3, and then so by theorem by theorem 5.2 and 5.3, we need only count the number of permutations with the disjoint cycle of the form A1, A2, A3, A4, A5, A6, A7, right? Now first consider the cycle. First consider A1, A2, A3, A4. Cycle A1, A2, A3, A4. And although the number of ways to fill these slots is number of ways to fill these slots is 7.6.5.4. This product counts the cycle 4 times. This product counts the cycle 4 times. For example, the 4 cycle 2741 can also be written as is similar to 74127, 1274, whereas the product 7654 counts them as distant. Whereas the product 757654 counts them different. Okay. Likewise, likewise, 321 expression expression for A5, A6, A7 counts the cycles A5, A6, A7, A6, A7, A5, and A7, A5, A6 is distant. Even though they are equal in S7. Even they are equal in S7. Adjusting for 3 multiple countings, we have adjusting we have 7.6.5.4 and 3.2.1 divided by 4.3 is nothing but 420 elements of order 12 in S7. Thank you very much. Okay, here we will end our this part of the lecture.